if you have something like x1, x2, x3, and then y. So just imagine the green fish length, height, and width, something like that. Okay? And then y is the weight. So you'll have the first example of the value of x1, x2, x3, and then y1. No, sorry. I just realized something. Okay. Sorry, I hate subscripts, but I guess I don't have any choice. I'll just do x1, 1, x2, 1, x3, 1, and then y1. x1, 2, x2, 2, x3, 3, 3, 2, y2, the next item in the data. Then we had like 35 lines, right? So we have something, x1, n, x2, n, x3, n, yn. And given that data set, by multiple regression, I'm saying the following. I'm trying to say that the predicted value for y hat is equal to some beta 0 plus beta 1, x1, plus beta 2, x2, beta 3, x3. Okay. Finding the best fit coefficients beta 0, beta 1, beta 2, beta 3 is our goal. And we determine the best fit by saying that the difference between the actual value of y minus the predicted value, you square them. This is called the sum of squares of the error, right? And we want to reduce this. We want to minimize this. So we can do a similar kind of calculation that we did with calculus. We just take the derivative with respect to beta 0, beta 1, beta 2, beta 3, and you just do all the calculations, and you end up with a system of equations which can be solved. And then that calculation, I don't think I can do it. So I'll just write down the final solution if you did it. Okay? So what you do is you define this x. So this is an x in boldface. It's not that x. Okay? I'm using boldface because it's a matrix. And we put a matrix by attaching a 1 here. Okay, so this x is like 1, 1, da da da, 1. And then the value x11, x21, x31, and then all the way down till x1n, x2n, x3n. So you get this big matrix. I can't make everything bold all the time, so I'll just put x for now. Hopefully you don't confuse this one with the random variable. We also use capital for random variables, right? So what we know is that the beta 0, beta 1, da da da, beta k, if you have k number of predictor variables, then this is your column vector of betas. And this is given by first taking x, taking the transpose. You know what transpose is? Yes? Do you know what a transpose is? This is called a diagonal, right? And you switch this around, okay? So if you had n number of columns, then k plus 1 number of rows. No, sorry. This is, yeah, n number of rows and k plus 1 number of columns. That's what this is. So this is a n by k plus 1 matrix. And if you take the transpose, it will be a k plus 1 by n matrix because you're switching like that. Okay? So that's what x transpose is. And then you multiply this by x. And you take the inverse. And you take x transpose times y, where y is this matrix. Okay? So y is the matrix of y values. So that's what you get. Okay? And going from here to there is just another big calculus question. Now, since I have more time, let me explain just a little bit more. So I want you to verify that this is indeed true by thinking of the simple linear regression. So a few lectures ago, we had the formula for the simple linear regression, right? So what was the simple linear regression formula? Beta 1 was given as SSXY divided by SSX, right?
Plus, yes.
And then beta 0 was obtained by doing y bar minus beta 1 times x bar. And then if you stick this in here, then we have a formula. We can just replace beta 1 by this SSXY over SSX x bar. So that's what we obtained from the calculus, and I think it will be helpful if we get the same exact formula using this one for this case. Okay, so let's try that. It's kind of fun, and it's much better than trying to get that formula from differentiation. It's just, you don't want to do that. Yeah, you wouldn't be able to go home if we did it. Okay, so just bear with me here. Okay. All right, so since we have a simple linear regression, that means we just have one predictor variable. So this is going to be your x. That's your y. Okay. So now let's try to calculate x transpose x. Because now we have to calculate the inverse of it. So what is that? That's if you take the transpose of this, the columns will become rows, right? So instead of having a column of ones, we'll get row of ones. So 1, 1, da 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 1, x1, x2, xn. See, I don't have to put 1 here anymore. It's just x1, 2, and then xn. Okay, that's what we have, and then times 1, 1, da 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 1, x1, da 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 xn. All right, so hopefully you didn't forget how to multiply matrices. You know how to multiply matrices? What do you get on the first one? Here.
1.
Well, 1 times 1 plus 1 times 1 plus... How many 1s do you add?
Oh, as many as there are.
What do you get? N. And then if you do this times this, what happens? Sum of xi's, right? And same thing happens here as well. How about the last one? x1 times x1? Just like that, right? So sum of x squared. Okay. That's what you get. Okay. Do you remember how to invert this matrix? A, B, C, D. How do you do the inversion? 1 over AD minus BC, and then you switch these two around, right? And then negate these two, right? That's what we need, which means we first have to calculate the determinant. So let's do that. Calculate it over here. The determinant of xt times x is this times this, n times x squared, xi squared, minus sum of xi squares. Now that looks really familiar. If you factor an n squared out, you get 1 over n sum of xi squared minus Can you guess what this is? This is the average of x squared What's this? This thing is average of x, and then you square that, and you're subtracting that. What's that?
Variance.
It's the variance, right? So you have n squared times the variance of x, and I don't like using this x because that's not the same as the matrix x, so it's dangerous, so I'm not going to use that, but rather, I know that n times the variance of x is what we call sum of squares of x, okay? So we're going to use n times variance of x, and then we're going to change that into n times sum of squares of x. Okay? So that much is done. And therefore, since we now have the determinant, I can now calculate this. So what is x transpose x inverse? According to the formula I raised, it's 1 over the determinant, which is n times sum of squares of x. And then you have to switch these around. So sum of x squared, and then you have n. And these have to be negated. But then if I divide everything by n, you get 1 over sum of squares of x, with this one being 1 over n times xi squared. So what's that? That's like, I guess I should just write it. It's tempting to write down e of x squared, but I can't do that because x means something else. But then this one's easier. What is that? If you add everything and divide by n, what's that? X bar. So you have negative x bar, and then n divided by n is 1. Okay, great. So now we have computed this much, and therefore what's left is this. So let's continue with that calculation. And I don't have any room, so I guess I'll have to write over here. Okay. So what I have is x transpose x inverse times x transpose y is going to be equal to 1 over sum of squares of x, and then 1 over n sum of xi squared minus x bar 1 times, and then x transpose is this matrix 1, 1, 1, and then x1, x2, xn. That's the x transpose, and then y is the y1, da da da, yn. Okay, so that's the y matrix. Again, just do the matrix multiplication. This times this gives you what?
Sum of y.
Sum of y's, yes. So 1 over n, summation of xi squared, minus x bar, 1, and then you have sum of y's. And then this times this is sum of
X times
xi, yi. Oh, we've seen that before as well. So just to remind you, let me write down a formula that we've done a long time ago. So sum of squares of xy was defined as summation of x minus x bar, xi minus x bar, times yi minus y bar. But there was a formula for this, which was that this is same as summation of xi yi, okay, minus it was n times summation of xi, summation of yi. Okay. And this is really a special case. I mean, I didn't write it like this. I actually gave you covariance, which is more like 1 over n of this. Let me see. Sorry, this should be x bar, y bar. Let's see, it's n. Right, so, okay. So this is the formula for the covariance, which is this thing divided by n, okay? But this is what we know. Okay? And it's nice because I actually need beta 1 to be SSXY, so something's working. Okay? So let's continue on, and hopefully everything works out. So if I do this times this, it's going to be 1 over SSX, 1 over n summation of xi squared summation of yi. Well, 1 over n times yi, that's good, that's y bar. Okay? And then this times this gives you minus x bar summation of xi yi. And then this times this, well, I guess I want to rewrite this as n times y bar. Okay, that's better, okay? So it will be negative n times x bar y bar. And then finally, 1 times this is plus summation of xi yi. Look, this one, exactly this one, right? So we have 1 over SSX of SSXY on the bottom. On the top, it requires a bit more work. This is a summation of xi squared minus x bar. I think should be n times x bar squared times y bar plus n bar x bar squared y bar. Okay, so you have to rewrite this single thing by subtracting and adding this, and then this much will be, this is really sum of squares of x. So what you get is sum of squares of x times y bar plus then this thing, if you factor the x bar out, it'll be minus x bar. And then once you factor the x bar out, you get this again. So it's again SSXY. Okay, so now let's read off beta 0 and beta 1. So what is our beta? See, remember, this is our beta 0 and beta 1, right? So the first row is your beta 0. So let's read that. Beta 0 is what? Beta 0 is this divided by this. This divided by this cancels, so it's y bar minus x bar times SSXY over SSX. And beta 1 is simply this divided by this, so it's SSXY over SSX. Okay? And it verifies our formula before. Okay? So I just wanted to demonstrate this. There's some other things that you can read off from here, but I guess we're out of time.